All right, today we're talking about logarithmic functions, which is actually going to be the inverse of our exponential functions. By the end of today, we'll be able to change from logarithmic to exponential and back. We'll be able to evaluate a logarithm, and we'll be able to use our basic logarithmic properties. So let's start with what is a logarithm. It is the inverse function of our exponential function with a base b. And so we can see where they match here. Our exponential, like we were seeing yesterday, is something like a b raised to the y equals some x value. If you notice where those things show up, b, the base of our exponent, becomes the base of our logarithm. The exponent becomes what our logarithm equals, and what our exponential equaled is what is inside your logarithm. So when I read a logarithmic equation, I always think that b raised to some number will equal x, is the way I think. I think exponentially, but those statements are equivalent to each other. And so we will see that we are flipping back and forth between logarithmic and exponential frequently, especially towards exponential, because that's the way that our brains tend to think about how to solve things. Another thing that you'll see is that base e. We learned about e yesterday being that irrational number. If our logarithmic function has a base e, it has its own special notation, which is this ln. That isn't like an L, N. It is a letter, not a number. And it stands for natural log, as you see at the top here, natural log. And so anytime that you're supposed to have a base e, you will instead not write the e as a base, but you'll use the notation of ln. So changing from logarithmic to exponential, the key is the base of the logarithm is the base of the exponent. That's all you got to always remember. So if we are given the logarithmic function, start with the base, and the base comes from the base of our logarithm. So if we have log base 7, writing this in exponential format, we would use the same base, and what it equals is always going to be your exponent, and then that will equal what was inside the logarithm. So this would be 7 raised to the third equals x. So let's do that one more time here. Take our base raised to what it equals what's inside. So it'd be log base b of 25 equals 2 would become exponentially b raised to the second equals 25. Continuing to change from logarithmic to exponential, I'm just seeing some other formats here. So again, whatever our base is, raised to what that logarithm equals is going to equal what's inside here. So this would be 4 raised to the y equals 26. And then finally, we start seeing some natural logs show up. And I don't have a base to circle here, but remember, if I were to zoom way in on this, that's like a base e. They're never going to write the e there, but if it's a ln, we know that base is e. Raised to the 8th will equal what's inside. So this would be e raised to the 8th equals x. All right, so going our other direction again, make sure your exponential is that we start with the base. So the base of our exponential is 12, becomes the base of our logarithm. So I can take that 12 and I write it as a small number next to my log. Whatever it equaled is going to be what's inside, so that x moves inside of my logarithm, and your exponent becomes what that equals. Notice the 2 goes on the outside here. Similarly, on this next one, start with the base. Log base, base of our exponent. So log base b of what it equaled equals the original exponent. And then on this next one, again, I would start that same way. And as I go to start this, I would say log base, base of my exponent, but I'm about to write a log base e. So instead of writing log base e, I replace that with ln, natural log, of what that equaled equals the exponent. All right, so evaluating logarithms, this is when I really do think exponentially, because that's the way my brain works a lot better, is that to evaluate my logarithm, this is saying that log base 2 of 32, 2 raised to something, gives me an answer of 32. That's what this logarithm is saying. And when we evaluate it, our answer is whatever that something is that 2 would be raised to give us an answer of 32. Now, if you don't know what that is, think about the powers of 2. 2 to the first, 2 squared, times 2 again, so that'd be 2 to the third would be 8, 2 to the fourth would be 16, and 16 times 2 is 32, so that's 2 to the fifth. So evaluating this, we would get an answer of 5. 2 to the fifth would be 32. Now in this next one, it looks a little weird because there's nothing written here. When we are missing something in our logarithm, but it does say the word log, the standard is base 10. So if nothing's written there, it's a 10. And again, this is going to say 10 raised to something equals 1,000. And we got to figure out what that 1,000 is. And again, as I work my way out here, 10 to the first is 10. 10 squared would be 100. If I take it times 10 again, I would add a 0 and I get 1,000. And so there's our answer there. Is that log base 10 of 1,000 is 3. All right, so then seeing some variations on this. How do we get a fraction? When I've got a base of something, 7, and I raise it to some number, and my result is a fraction, okay? Well, first of all, I know how to get from 7 to 49. 7 squared gives me 49, but what is it that takes a number and moves it down into the bottom of a fraction? And that would be having a negative exponent. And so this 49 would be the same thing as a 1 over 7 squared. So being in the bottom of that fraction, if I move that back up to the top, you can see that that would be 7 to the negative 2. This number right here, to get us a fraction from a non-fraction, would be a negative exponent. Okay, so whatever would give us the denominator, but then negative to be a fraction. So our answer on this would be negative 2. Okay, so then another one we have is how do we go from a big number to a small number? So this time my base is bigger than my answer. I'm starting with the number 25. I'm raising it to something and getting a smaller number of 5. And what I want you to do when we have something like this is think backwards, okay? What if I were going the other way? If I were raising 5 to something and getting an answer of 25, that one's a little easier for us to think of. That would be a 2, right? 5 squared gives me 25. But if I'm trying to undo that, I want to move from 25 down to 5. What happens is, again, we need that to be the opposite of squaring, and it ends up being square rooting. I picked 25 and 5 because we are pretty familiar with those two. And if I wanted to move from 25 to get 5, I would have to square root it. And then if you look at what square rooting is as an exponent, that is 1/2. So now let's work our way backwards again. How can I do this backwards? So look at our result here. 25 raised to the 1/2 gives me 5. And so to move from a big number down to a small number, it will be a fraction exponent. And to decide on that fraction, you're going to think backwards. Of whatever I would raise the smaller number to get the bigger number, it becomes the denominator of our fraction. So let's look at a second example of something like that. What if I had something like log base 81 of 3? So 81 raised to something gives me 3. Well, I know that that something is going to be a fraction. And then I have to think of my bottom of that fraction, 3 raised to what gives me 81. And so if I think through my powers of 3, 3, 9, 27, 81, 3 to the 4th. And so that denominator would be a 4. Okay, when we're working with radicals, again, we want to make them look like fraction exponents on this. So 3 raised to something gives me the 7th root of 3. Well, if I am looking at a radical here, 7th root, remember that we can always write that as a fraction exponent, which would be like 1/7. Well, 3 raised to something gives me 3 raised to the 1/7. Well, then those would match, right? If it's the same base, their exponents have to be the same, and we would get a 1/7. And so what I would just encourage you to do is anytime we're working with radicals is write them as fraction exponents. Okay, so our basic log rules are going to say this. If I have a log base anything, and that matches what we get on the inside, so log base b of b, in order to do that, b raised to something to give me b, that something would have to be a 1. And so notice this will always equal 1 if these two match. And again, think exponentially. B raised to the first equals b. Now think of this again exponentially, log base b, and there's a 1 inside. The only way I can get a 1 there is to raise what is the base to the 0. So again, think exponentially, b raised to the 0 would give me 1. So if there's a 1 inside, automatically that's going to equal 0. All right, some other logarithmic properties here. If your base matches the base of an exponential inside your logarithmic, your answer will be whatever that exponent is. This is not what's happening, but it's kind of like those bases are canceling out and you just get the exponent. Similarly, if we have something written in exponential and again, the base of our exponent and the base of our logarithm match, you'll notice your answer matches whatever other number is there. So let's look at a very quick example. If we have something like a log base 5 of 5 to the 8th, I don't need to know what 5 to the 8th is, because if the base of my logarithm and the base of my exponential match, our answer will be whatever other number is in the problem. All right, so at this moment in the video, I would pause. What we just went through were all of these general properties. So this column right here. And what you'll notice is that I also have these listed as your common logarithmic properties, which would be your log base, and I'm going to put this in parentheses, log base 10, where it doesn't have a base written there. And then also your natural log, which would be your log base e. They are all the exact same 4 properties we just looked at on the last page. So if I zoom in, last 2 pages, we just looked at these again. That if we have a 1 on the inside, it's going to equal 0. If your base and the inside match, it equals 1. If the bases match either logarithmically or exponentially, that you get whatever other number is in there. And so if that base specifically becomes a 10, that's how those logarithmic functions or logarithmic properties change their look a little bit, the same property though. And if our base becomes e, remember that's what natural log means, base e, same 4 properties. But again, look just a little different with specific base of e. So I would take some time right now, pause the video and get this chart put into your notes so that you can have a quick reference for the logarithmic properties. Just seeing some of those properties in application here. You can see these are the inverse properties here. We have the same base. Remember, natural log, and I'm going to write this out a little bit bigger, is, which will never be written here, but it is base e. And so what we're seeing is the base of our logarithmic and the base of our exponential matching. And if that's the case, whatever other number is there becomes our answer of 2. Because this means that e raised to something gave us e raised to the 2nd. And so we end up getting that 2. Similarly here, on the second one, we've got a base of e in our exponential. We've got a base of e in our logarithmic, which again would never be written this way, but natural log is base e. So you can see that the base of our exponential and the base of our logarithm match, which means our answer is whatever other number is in that problem, which would be 4. And our last one of evaluating is going to just see again a couple other properties here. A 1 on the inside. We've got a 1 on the inside, and I don't have a base written. So remember that no base written means that it is 10. 10 raised to something gives me an answer of 1. Well, it doesn't matter what that something, it doesn't matter what our base is, that something is going to be a 0. So if we have it a 1 on the inside, our answer would be 0. Similarly, on this next one, now I have a base of 5. 5 raised to something gives me an answer of 1. And in order to get an answer of 1, I have to raise whatever my base is to 0. All right, your assignment today is on MyMathLab. Please feel free to rewind the video to any part that you need to rewatch or didn't get notes taken for. But you are looking at assignment number 45 on MyMathLab.